We are given a few species, asked to classify them as electrophiles or nucleophiles. If we consider methane and hydrogen, these have no lone pairs of electrons, they are not electron deficient, they are saturated, and therefore they are neither electrophilic nor nucleophilic. CH3Cn and CH2 double bond O have an electrophilic carbon center, and the electronegative nitrogen or oxygen can become the nucleophilic site. By electron redistribution, carbon can get a positive charge and a nitrogen or oxygen can gain a negative charge, which will make carbon the electrophilic center and the nitrogen or oxygen the nucleophilic center. So these can act both as electrophilic and nucleophilic reagents. We have ethoxide and iodide, which are both anions, have lone pairs of electrons. In ammonia also, there is a lone pair of electrons. So these reagents would act as nucleophiles. Cl plus is a cation. BF3 and CCl2 are not cations, but what is common to all these three is they are all electron deficient. They all have only 6 valence electrons. So they can be electrophilic reagents. NO2 plus with a charge and electron deficiency is a very strong electrophile. The oxygen atom attached as a nucleophile, but its nucleophilicity is masked by the very strong electrophilic tendency. So this acts like an electrophile. In HCl, we have a classical example of a Bronsted acid. This can give a proton. A proton is electrophilic. It no doubt gives a Cl minus also. But being very stable, chloride is a very weak nucleophilic reagent. And therefore, HCl becomes an example of an electrophile. SiF4 is given an octet. It has formed 4 covalent bonds. It has 8 electrons in the outermost orbit. Silicon is in the 3rd period in the periodic table and can make use of the d orbitals. It can expand the octet and accept electron pairs. It can, for example, combine with F minus to produce SiF6 2 minus. So SiF4 is an example of electrophile.